Hello and welcome to the 25th lecture. So today we're going to be talking about curve sketching, which is a topic that we've discussed before, but now we can discuss it in more detail because we know L'Hopital's rule. Okay, so when we discussed this before, we broke up the information that we can obtain into three kinds. Into the zeroth order kind, which is the kind which we get without taking a derivative, so zeroth order. And then we have, let's put it over here, the first order, the information we get from taking one derivative, and then the second order. Okay. Now let's be a bit more systematic by what we mean by the zeroth order. So there's four pieces of the zeroth order information that we have to obtain, and they are the following. So let's categorize them like this. So 0a, it's the main. So first we want to think about where this function is defined that we're trying to sketch. Let's write 0b. And let's do symmetry. And periodicity. So, if our function satisfies this, for example, f of minus x is minus f of x, then it's symmetrical across the y-axis. And so, for example, whatever we have going on here, we have a mirror image across the y-axis. Okay, that's not a very good picture, but you know what I'm trying to do. Okay, so it's symmetrical across the y-axis, and we only need to figure out what's happening across one side because the other side is just immediately copyable from the side that we figured out. So this is called an even function or symmetric. Or we can have anti-symmetry. And this is like what happens when we take our function and whatever it's doing. So it's doing something like this. Then we reflect it across the y-axis, and then we reflect it again across the x-axis. So something like this. So for every x, suppose we have an x like this guy here. Then if we go to minus x, then this value here, f of x, instead we find it here, minus f of x right here. Okay, so if we have this property, then again we only have to worry about one side. And obviously if it's periodic like a trig function, then we only have to worry about what it looks like on some little interval because it just keeps repeating itself from that point onwards. So that is 0b, those kind of broad properties. Okay, 0c, asymptotes. Horizontal and vertical. Later we're going to learn about something called the Slant Asymptote. And 0d, x and y intercepts. Where our function crosses the x and y axis. Okay. It's definitely better to start with domain and then symmetry, periodicity, and then you can do asymptotes or x and y intercepts in either order. Those don't matter. Okay, so there's 4 distinct pieces of information from the first order. And after we do the first order, there's the second order, which is just as we've done before. Second order. Intervals of increase or decrease, local max and min. Okay. And then third order, sorry, not third order, second order. Intervals of C up. C down. Point of inflection. Okay, so the first order and the second order are exactly as we've done before. The reason we have this section on curve sketching now after L'Hopital's rule is that for understanding the horizontal or vertical asymptotes, it's an advantage to actually have L'Hopital's rule. There are times when we can only understand these limits by using L'Hopital's rule. So now that we have L'Hopital's rule, we can get all the information possible up to second order that we want out of our function. And that is what we're going to learn. Okay, so let's do our first example. This function. Y of x is equal to 2x squared over x squared minus 1. Okay, solution. So, 0th order first. What's the domain? So the domain is everything except where x squared equals 1. So domain has 3 connected intervals. We have minus infinity to minus 1, minus 1 to 1, and 1 to infinity. That's our domain. Okay, that's part A. Then what? Well, I want to see if there's any symmetry. So if we look at this guy, notice y of minus x equals y of x, because the x squared doesn't notice what if we have positive, if we have x or minus x. So it's symmetrical. Symmetric function. So we only have to think about either the positive numbers or the negative numbers, and then we can just copy it across the y-axis and then send everything else. Okay, symmetric function. Now let's think about the intercepts. So let's think about when it crosses the y-axis. So it will cross the y-axis when y of x equals 0. So let me first write down what we're doing. So, and what I just said was wrong anyway. Intercepts. So when does it cross the y-axis? It crosses the y-axis when x is equal to 0. No? So y of 0 is just 0 because of the nature of this function, right? So it only is going to cross, it is only going to cross the y-axis at the point 0. And where does it cross the x-axis? It crosses the x-axis when y of x is equal to 0. So if y of x equals 0, If you look at this thing, the only way this thing can be 0 is if actually x itself is 0. This implies x equals 0. So it only crosses the x and y axes at one point, and that's the point 0, 0. So that is the only intercept. Okay, so what do we got? We got the main, first thing, we got symmetry, with the intercepts, and now we need the asymptotes. Okay, so if we look at our function here and we let x tend towards infinity, we see that for very, very large x, this thing on the bottom, x squared minus 1, isn't really noticing or caring about this minus 1. It's a very, very, very unimportant thing for incredibly large x. If you take x to be 100, then 100 squared is 1,000, so that's like 2,000 on the top. And start again. If we take x to be 100, then 100 squared is 10,000. So it's like 20,000 on the top, and it is like 10,000 minus 1 on the bottom, right? Which is incredibly close to just the number 2. And as the larger we take the x, the more it looks like 2. In fact, it looks more and more just like 2x squared over x squared, right? So this is the section horizontal asymptotes that we did before. If you want to be very, very cautious, you can factor out an x squared from the top and the bottom, and then you'll see the following. Oops. And clearly the limit of this thing is going to be 0, so the limit as x either goes to plus or minus infinity, by symmetry we know they're going to be the same limit. We also can see that it's not going to matter in this expression. So we have horizontal asymptotes. Okay, let's start to block in the information. Horizontal asymptotes will be at 2. Here we go. Let's put these lines out here at 2 to indicate the horizontal asymptotes. Okay, and if we look at this expression here, we also see that when x approaches either plus or minus 1, we are going to have a vertical asymptote, and we're going to have to figure out which one is which. So let's consider this limit. The limit as x goes to 1 from numbers bigger than 1 from the right-hand side. So on the top here, it looks more and more like the number 2. And on the bottom here, we're going to have a number which is just a little bit bigger than 1, subtract 1. Because if we have x just a bit bigger than 1, and we square it, we still have a number just a little bit bigger than 1, and we subtract 1, so we have a very small positive number. So we see that the limit as x goes to 1 from the right-hand side is going to be infinity. And also the limit as x goes to 1 from the left-hand side, let's figure this guy out. So if x is a number just a little bit smaller than 1, then x squared is also a number just a little bit smaller than 1. So therefore x squared minus 1 is a number which is very, very small and negative. Yeah? So on the top we have a number which is very close to 2, on the bottom we have a very small negative number, and it gets smaller and smaller as x approaches 1 from the left-hand side. And so this limit here is going to be minus infinity. And that's it. So let's block in the information. So here is, say, 1, and this is minus 1. And as we approach from the right-hand side, we've got this vertical asymptote happening here. So let's put in a line to guide us. Like this. Okay. And what we see happening is that this thing is doing something like this, most likely, right? Because as we approach 1 from the right-hand side, it's blowing up to infinity. And as we approach 1 from the left-hand side, it's going down towards negative infinity, so it's somewhere like this. We also know it's crossing 0, 0, so we can connect up with the stuff we know. It looks somewhat like this. We also know it's symmetrical, so we're going to copy everything we see across reflecting across the y-axis, and we see just from zeroth order information that we anticipate some function somewhat like this. Yeah. Cool. So that's zeroth order information. All right. Now, that's as much as we can get without taking the derivative. So we're going to take the derivative, see what we get. So y prime of x is equal to, so let's put everything over the bottom guy squared. X squared minus 1 squared. Differentiate the top, we have 4x, leave the bottom alone, minus, leave the top alone, differentiate the bottom. Okay, what do we have? We are going to have 4x to the power 3 minus another 4x to the power 3, so that's going to cancel. And we're just going to have minus 4x on the bottom, on the top here. So we have minus 4x over x squared minus 1, everything squared. Cool. So what do we learn about this thing? Well, we learned that the sign of the derivative is just determined by the numerator, because the bottom is either going to be 0 or it's going to be positive, so it's not going to affect the sign. And we're interested in where the denominator is non-zero, because that's only the points of the domain, right? We only care about points in the domain. So we only have to look at the numerator to see what is going to be the sign of this thing. So it's going to be negative for every x which is bigger than 0, and it's going to be positive for every x which is less than 0. So y is increasing for x which is less than 0, and x not equal to minus 1 is not defined there, and it is decreasing for x bigger than 0 and x not equal to 1, again, because it's not defined when x equals 1. And that makes sense with what we see, right? If we're out here towards negative infinity like 2, we can be increasing all the way like this, yeah? And then on this part of the domain, from minus 1 to 0, again, as we get very, very close to minus 1 from the right-hand side, we're like some very negative number. And then we're increasing until we hit 0. Yeah? And then from 0 to 1, we are decreasing, which makes sense. It's consistent with that. And we see we're decreasing here as well. Yeah? Cool. Note also that this is only possible because we paid attention to the fact that we have this function has its domain in these 3 separate intervals. If you were not thinking about what you were doing and you were just calculating, and this is a mistake I've seen many times, you might get to this thing and think, okay, the horizontal asymptote is 2, and this is a negative derivative, so it's got to be, this is a positive derivative, so it's got to be consistently increasing, but then you're stuck because you're around 2 and you've got to be increasing it, but you know it's going to be 0 at 0. Right? But since you've paid more attention and you've realized it has vertical asymptotes, it's not defined at minus 1 and 1, then sure enough, it can be increasing, and everything can fit together, and it makes sense. Yeah? So we did some examples of some discontinuous functions, some functions with discontinuity, where the domain wasn't the entire real line before, which exhibited this phenomena already, but we see it here again. Okay, so that is first order, and we have to finally see if there are any local maxes and mins. So local maxes and mins will only occur when the derivative will change sign, right? The derivative is only going to change sign as we go across 0, yeah? And if we go across 0, so for negative, we are positive derivative, and then 0, we are 0, and then we are, for positive x, we are negative derivative, so it goes like this, yeah? So we expect to have a local max at 0, and we do have a local max at 0, and the local max at 0 is the number 0. So local max at 0, and 0 is the local max. Cool. All right, so that is all the first order information. But we still have the second order, so let's try and erase some part of this so that we have some space to calculate the second order. Okay, let's try and squeeze everything in this corner. All right, so our derivative is this thing. We want to calculate the second derivative. So everything under the bottom guy is squared, so we have x squared minus 1 now to the power 4. Differentiate the top guy, leave the bottom guy alone. So we have minus 4 times x squared minus 1 squared minus. Leave the top guy alone. So we have minus 4x. And now we're going to differentiate the bottom guy. We're going to have 2 x squared, x squared minus 1 times 2x. Yeah. So what's that? Well, I want to factor out an x squared minus 1 from the top and cancel it with the bottom. And then that's just going to leave me with minus 4 x squared minus 1. And here, when I factor out this x squared minus 1, all I'm going to have left is 2 times 2 times 4 x squared, so 16x squared, right? And the minuses will cancel, so it's a plus 16x squared. And then this is the x squared minus 1 now to the power 3, because I've cancelled this x squared minus 1 power from the top. And then I see that this thing just becomes 12x squared plus 4. On the bottom we have x minus 1 to the power 3. So the top is always positive, right? So that thing is not determining the sign. The sign will just be determined by the sign of the bottom, right? So y double prime of x is going to be positive whenever the bottom is positive. And the bottom is going to be positive so long as x squared is strictly bigger than 1, right? And that's the same with having the absolute value of x is bigger than 1. And second derivative is negative whenever x squared is less than 1, which is the same as having absolute value of x less than 1. So I should say 4. Is less than 1. Okay, cool. So it should be concave up for every, or on the regions where absolute value of x is bigger than 1. So that's from minus infinity to minus 1, and from 1 to infinity. And sure enough, this thing looks concave up. Yeah? We can make it be concave up, and concave up like this, right? Because it's curling above its tangent line. So let's sketch in some tangent lines just to show you. Some tangent lines like this, and like this. Like this, like this, and like this. And it is concave down for x between minus 1 and 1. Right? Because that's exactly the set of points with absolute value of x is less than 1. And if we look here, yep, this is concave down. It is underneath its tangent lines. I can see it like this. So everything makes sense. Huh? Final thing, points of inflection. So a point of inflection is a point on the graph where the graph goes from being concave up to concave down, or vice versa. sure enough, we have that this thing goes from concave up to concave down, but it's not doing this across a point of the graph, right? It has this vertical asymptote here where it goes off to infinity, and then it's not defined -1, and then on this new part where it is defined from -1 to 1, it is concave down. So there's no point on the graph where it's actually flipping from concave up to concave down. P of i's and do not exist. For y. And that's it. So we've understood everything about this function. And again, if we'd messed up in some way, there's a high likelihood we couldn't have put all this information consistently together. We can put it all together. It's all making sense. This is kind of like a detective novel where you have these clues and you build up the clues as to the actual nature of this graph. And when you have all the clues, you can put all the picture, all the stuff together, and it's a coherent thing that makes sense. You have the complete picture, and that's what we've done for this guy. Okay, cool. We'll talk about what a slant asymptote is, and we'll do another example, and that'll be it for the day. So let me erase the board, and we introduce slant examples, slant asymptotes, sorry, and then we do an example where there is a slant asymptote. Okay, let's talk about slant asymptotes. So we say f has a slant asymptote. I'm going to abbreviate asymptote to asym, given by, say, mx plus b, if and only if the following is true, that the limit as either x tends to infinity or it could be minus infinity, f of x minus this function mx plus b is equal to 0. As always, the picture clarifies this. Let's put a graph here. So suppose this is the line mx plus b, so this is the height b. We can have a function which is doing some sort of weird stuff, but ultimately as we get further and further out towards infinity, it's tending more and more towards this line here, which is this mx plus b line. So obviously the slope is m, and let's make this thing look more like it's tending towards the intercept, so it's looking more and more like this. Cool. So this is just a kind of a generalization of horizontal asymptote. So if m was just 0, this would exactly be a horizontal asymptote, and we'd say that b was a horizontal asymptote. But instead of this, we are allowing it to have a slope, and that's what it means. That's all it essentially is, right? And it's not particularly difficult to visualize. And the most common examples are things like f, which is a rational function where the degree of the polynomial on top is just 1 bigger than the degree underneath. And then for very large x, it looks more and more just like a linear function which goes through 0. And that's the example we will do here. Well, I should maybe complete this. If and only if this is true, or the limit as x goes to minus infinity, f of x minus mx plus b is equal to 0. So just like we can have two horizontal asymptotes, we can have two distinct slant asymptotes. So this is the example we will study. So example, f of x is equal to x to the 3 over x squared plus 1. Okay, cool. So we do the same thing. We're going to break this down using a strategy of going 0th order, 1st order, 2nd order. Okay, and 0th order. What is a really good idea is if you kind of nail down the fact that there are 4 things on the 0th order. If you remember that fact, just that there are 4 0th order things we have to find out, then that's pretty much all you need to remember, because you will eventually come up with all of them. And then 1st order it's easy, it's clear. There's only 2 things to do with 1st order: intervals of increase, decrease, local maxes, local mins. And 2nd order is also easy: intervals of C up, C down, points of inflection. So you only really have to remember one thing. 0th order has 4 things to find, and then you'll come up with them gradually. Yeah. So this is our guy. 0th order. What are the 4 things? The first thing is domain. So domain is everything. This thing is defined everywhere. Domain is the whole of the real numbers, which we denote by this, everything. There's no point where this thing is not defined. Okay. Second thing, symmetry. This thing is anti-symmetric. So if we look at f of minus x, it's not, the minus x is not noticed by the x squared, but it is here. So this is the same as minus f of x. So we can reflect across the y-axis and then reflect that side across the x-axis to find out what's on the other side. Yeah? So we only need to understand for positive x and for negative x because of this property. Cool. So 0th order, symmetry. Okay, what next? So we have domain, we have symmetry. Let's do x and y intercepts. So where is it going to cross the x-axis? So it crosses the x-axis when f of x is am I getting this wrong again? It's going to cross the x-axis like this when f of x equals 0. Yeah. So if f of x equals 0, when can that happen? That can only happen if this thing's always bigger than 1, right? So it's only going to happen if x is equal to 0. So it's only going to cross the x-axis at this point here, x equals 0. Yeah? And when is it going to cross the y-axis? It's going to cross the y-axis when x is equal to 0. So what value will we have when x equals 0? We put x equals 0 into this, we just get 0. So and f of 0 equals 0. So it's only going to cross the x and y-axis at just one point, which is the point 0, 0. So x, comma y intercepts at 0. Cool. Okay. Final property, and that's the asymptotes, right? So there are no vertical asymptotes. This thing on the 1 is always bigger than 1. It's never going to blow up to infinity at any finite point on the real numbers. So no vertical asymptotes. Also no horizontal asymptotes. As x tends towards infinity, this thing is clearly growing for positive x, and it's going towards negative infinity for negative x. Yeah? But if we look at this thing, then for very large x, then this guy is an awful lot like x to the 3 over x squared. Because again, the same reasoning, this plus 1 is very negligible for very large x. So it looks a lot to us that, like, for large x, this thing is just like x itself. So let me write that down. So asymptotes f of x kind of looks like just x for large x. Let's write large absolute value of x, so that includes for very positive x and for very negative x. Yeah? And how are we going to check that out? Well, let's just do some algebra. So f of x minus x, what's that? That is x to the 3. I'll write this better. X to the 3 over x squared plus 1. And then let us subtract x squared plus 1 over x squared plus 1. Yeah? because this is the same thing. And then what do we have from this? The x's, the 3's cancel, and we're just going to have just minus 1 over x squared plus 1. And this thing is going to tend to 0. So the limit as x tends to either plus or minus infinity of this thing, f of x minus x, is just this limit, which is just going to be 0. And that's exactly the definition of slant asymptote. That's what we have here. So in this case, the m is 1 and the b is 0. And we know on a large scale, this thing looks more and more like a linear function. And in fact, in one of the previous examples, we already saw something like this. So we didn't so carefully, explicitly define it as a slant asymptote, but we drew a picture which was like this, that for very large x, it looks like it's coming in like x from either side, either infinity or negative infinity. Okay, so we start to block in the information now. We have a lot of stuff. So what do we know? We know it's crossing at 0 right here. We know it's like x for x with the absolute value of x is very big. We know it's anti-symmetric. We will use that later. That's what we know. Okay, now first order. We differentiate. So we differentiate this expression. Here we go. Okay, everything on the bottom guy squared. Let's differentiate the top and leave the one alone. Minus, leave the top alone. Differentiate the bottom. Let's clean that up. So, what do we see? We see a 3x to the 4 minus a 2x to the 4. So we're going to have just x to the 4 right here. And we have a 3x squared right here. And that's it, right? Plus 3x squared. So what do we have? We have that this derivative always exists, and it is always positive when x is non-zero. And when it's actually 0, it's 0. So this is bigger than 0 if x is not equal to 0, and f prime of 0 is 0. So that is consistent because this thing is growing like this, right? So we can block in some information. So it's increasing, 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 and then it sort of flattens out somehow, and then it does like this. Okay, so that's all we have. There is no local maxes and local mins because this thing is never changing sign. So that's the whole thing of it. Okay, let's just write down the second derivative for the interests of time. So doing the question rule again, if we do the second derivative, cutting to the chase, we end up with this thing. Interest of time and space, because we're running out of space too. To the power 3. Again, this is the quotient rule. It's a bit more complicated, there's more terms, but you clean it up, you ultimately get this. Okay, let's look at this guy. All right, so now we have a bit more things to be concerned about, because we see that this thing, this thing on the bottom is always positive, so that thing's not going to influence the sign of the second derivative. But these terms on the top definitely will, right? So we're going to identify the intervals where the second derivative is either going to be positive or negative by finding out where the second derivative is actually 0. Yeah? And then we take away those points where it's 0, and then we just have some intervals. And on those intervals, it has to be either positive or negative because it's a continuous function. Yeah? So second derivative of x equals 0 if and only if we have x equals 0 and x squared equals 3, which is x equals plus or minus root 3. Okay, good. So what intervals do we have? Let's create a table like this. So intervals will be from minus infinity to minus root 3, from minus root 3 to 0. Oops. For some reason I'm not succeeding to erase with my finger today. Okay. From 0 to root 3, and then from root 3 to infinity. And then we put the terms we have. So we have 2x right here. We have, we don't need the brackets. We have 3 minus x squared right here. And then let's put the second derivative expression right here. Cool, so let's fill out the box. So here it's negative, here it's negative, here it's positive, here it's positive. That's easy. Here, if we have a number which is less than minus root 3 and we square it, then it's a number bigger than 3, right? And then we have 3 minus a number bigger than 3, it's going to be negative. Here we have a number which is strictly between minus root 3 and 0, and we square it, we get a number which is strictly smaller than 3. So we have 3 minus a number strictly smaller than 3, positive. Same argument here is also positive. And here we have a number which is bigger than root 3, so we square it, it's going to be bigger than 3. So 3 minus a number bigger than 3, it's minus right here. So we have minus, minus, positive, minus, positive, minus, positive, 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 and then minus. Cool. So let's put in this minus root 3, and this is a root 3. Then we have that it is concave up to this thing, let's say up to here, and it's out here, it's like x, so we can imagine that's happening, right? So it's like kind of curving upwards, say somewhere like this. And then on this part, it's going to curve downwards, concave down, which makes sense because it's got derivative 0 here. So that does make sense. Derivative will be decreasing and then will be ultimately 0 here. And then concave upwards, this part, which again makes sense because we're 0 and the derivative has to increase in order to get to the derivative, which is more or less like 1 over here. So it is indeed making sense. We do believe it's going up like this. And then it is concave downwards. So we have a derivative which is bigger than 1, and then it's going to be concave down, and it's sort of decreasing, 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 decreasing like this. And we see it has this anti-symmetry property because if you look at this part and you reflect it onto that side and then you reflect it again, you will see that you go from concave up to concave down as the calculation confirms. So all these pieces are fitting in. Yeah? Let's put in the tangents. So tangent lines, I should say. So concave up, so the tangents are underneath it like this, and then the tangents are on top like this, and then it's underneath like this, and then it is on top like this. Yeah? Okay, points of inflection. That is where we flip from being concave up to concave down, and that is definitely happening here, here, and here. There's a number of points of inflection, right? So the first one is minus root 3, and then what happens when you put minus root 3 into this function? We're going to have 4 on the bottom, and we have minus root 3, 3 over 4. Is that right? Let's check. So That looks good. All right, second point of inflection will be at 0, 0. And the third point of inflection will be root 3. And then root 3 times 3 over 4 right here. So we have 3 points of inflection on this graph. Cool. So, not too bad, right? This is not too difficult to work out. We figure out the slant asymptote by the same kind of argument we figure out horizontal asymptotes. We just say, okay, for very large x, what's the real structure of this thing? And ultimately, it's just the leading order term on the top divided by the leading order term on the bottom, which in this case just gives us something like x to the 3 over x squared, which is like x. And that's mostly the kind of example you'll have for slant asymptotes. And then we check it with some algebra. And again, it's a very analogous thing to the way we did horizontal asymptotes. And that's the only new thing that we learn or that we have to apply in this particular example. Overall, the new things that we have to learn for this section are, again, the 4 things we have to remember to note down for the 0th order properties. So again, they are domain, they are symmetry, they are the intercepts, and then they are the asymptotes, horizontal, vertical, and now slant. Get those things down solidly, then it's just stuff that we've already practiced, we already know how to do. If you've become solid on the section for L'Hopital's rule, which was how the derivative affects the graph, this shouldn't be too much additional things to learn and practice, and it's a very useful skill because I said lots of times that we need to know elementary functions really well because we build things out of them, and it's just what kind of it's like almost like learning verbs in a language, right? They occur all the time in sentences. So now we have this, you can figure out the graph of any elementary function. In fact, these are not, we can figure out fairly non-elementary functions with these techniques too. But all the elementary functions that we encounter, the logs, the trigs, the exponential functions, you can get a very good idea of them because now you can sketch functions. So if you don't already have this fluency with what elementary functions look like, now you can be sure you know what they look like and get to that point as quickly as possible. Okay, so that's it for today. I will see the Friday group on Friday. Have a great day.